Hi, welcome to Chemistry 1001, and we're talking about thermodynamics. This particular topic addresses the question, why does entropy sometimes seem to decrease? Here's a particular example. You might have done it when you were a student. You have a glass or a beaker full of concentrated salt and you balance a little string into it, and after a while you see a crystal growing on the end of the string. It's a classic way to grow crystals. Now, the thing is, the liquid is disordered, and it seems as if the crystal is forming out of nothing. In other words, the crystal, which is a very ordered form of matter, in the sense that the atoms are packed in a very regular array, as I showed you in the previous lecture for graphite and diamond, very regular and certainly not disordered arrangement of matter. Why does that form spontaneously? Because normally we've just said that entropy increases. That should say that all the time crystals should dissolve, not form. So a crystal naturally forms from solution. That is an entropy decrease. Here's another example. Ice naturally forms from water on a cold day. In other words, the disordered water becomes more ordered, solid form of ice. Now, a closer look at this reveals that whenever dispersal or order decreases in the system, such as here we have order forming, dispersal, the crystal is the components of the sodium chloride or whatever it is are coming out of the solution and condensing into this very ordered crystal here. Whenever dispersal decreases in the system, there's a corresponding process where it increases even more in the surroundings, and the sum of the entropy change from the system and the surroundings is always positive. So let's see how that works. Here's the system, here's the surroundings. This could be the crystal or a piece of ice, and here's the surroundings, the beaker or the water that the ice melts into. So when we consider not only the system but the surroundings, we will always find that the change in entropy is bigger than zero. The entropy of system can decrease. This number here can be negative, provided that the entropy change of the surroundings is opposite and bigger than the entropy change of the system, so that the sum of these two becomes positive. All right, so let's check it out. Let's work out what the entropy change of the surroundings is. The entropy change of the surroundings is simply the heat added to the surroundings divided by the temperature. The heat added to the surroundings is actually exactly the opposite of the heat lost by the system. That's conservation of energy. So on this top line here, we can add negative delta H of the system. Because, well, if a reaction in the system is exothermic, delta H is negative. That means heat, the energy of the system decreases and the energy of the surroundings goes up. So we have to have a negative sign making this whole quantity positive, and that is the heat added to the surroundings. Delta S of the surroundings is negative delta H of the system divided by T. Of course, we can consider endothermic reactions as well. Same formula, negative delta H on T, except that negative delta H is less than zero for an endothermic process for the system, delta H for the system. So what that means is an exothermic or endothermic process may be spontaneous, but it depends now on the entropy change of the system, as well as the entropy change of the surroundings, which itself depends on the delta H of the system. Got that? Let's have a look to make it clear. Here's the table. We make a table. There's only 4 possibilities, and we consider the different signs. Delta H for the system, delta S for the system. Delta H for the system allows us to calculate delta S for the surroundings by the formula, you guessed it, negative delta H on T. Delta S for the system, well, that's just itself. And we add these two things and we figure out whether the total is a positive number or not. Let's consider an exothermic process, first case. delta H system less than 0. That means delta S surroundings bigger than 0. Negative delta H on T is always positive, therefore is a positive number. We add delta S for the surroundings to delta S of the system. That happens to be positive because that's the possibility in this column. If we add two positive numbers, we get total delta S bigger than 0. That means the process is spontaneous. We can say categorically that an exothermic process will always happen provided delta S of the system is bigger than 0. That's true. But it's possible that an exothermic process may not happen. That's case 2. Here we have the same thing. We have delta S for the surroundings bigger than 0, but now we have delta S for the system less than 0. If we add these two together, add a positive number to a negative number, we will get, actually we don't know what we get. It depends on whether this positive number is bigger than the negative number. If it was, the process would be spontaneous. If this were smaller than the negative number, it would not be spontaneous. So the result depends on the relative magnitudes of delta H and delta S. It turns out that it's more favourable at lower temperatures. We'll talk about that later. And here's another case where the sum of the two is indeterminate. The final possibility is when an endothermic process is combined with a situation where the entropy change is less than 0. In this case, it's not spontaneous at all. And the reason is both of these terms are negative. Delta H less than 0 is a positive change in the system energy leading to a delta S for the surroundings which is negative. And if we add that to delta S of the system, both of which are negative, we'll get overall delta S negative. So that means that entropy change is negative and the system and the process is not spontaneous.